In this video, Dr. Jordan Peterson explains how to solve complex problems in life.
You could say that you respond to the world as if it's a predictable place, as long as it's doing what you want it to do, and then you respond to the world as an unpredictable place when anything happens that stops you from reaching the goal that you've determined to be relevant at this point in time. And so those are, in some sense, your two modes of operation. Then you could also add that if you're pursuing a goal, or embodying a little goal-directed personality, then things that facilitate movement towards that goal are going to be positive, and things that interfere with movement towards that goal are going to be negative. And when you understand that, then you've got some sense of how the fundamental emotional systems work. So, there's a set of phenomena in front of you that's too complex to deal with, and so what you do is you generate a low-resolution representation of it. And that low-resolution representation is actually what you see. It's not a concept, or you could say it's a percept. It's what you see when you look at something. So, for example, and then what you do with your words is you label the percept of the thing. And so it's like a double compression. That's in some sense what you're doing. So you have a complex reality, you perceive it in a low-resolution form, and then you label the perception, and that gives you a word. And so what you're doing basically is taking the world that you can understand, and you're putting it in smaller and smaller and tighter boxes until you have a box that's small enough and tight enough so that you can actually manipulate it. And that's a fine plan, except when it doesn't work. And so then the question is, well, what do you do when it doesn't work? And that is the question. Okay, so you could say, if you look at the top left-hand corner, I called that the thing in itself, which is a phrase from, it's a translated phrase from German philosophy, and the old idea was that, well, you never really have contact with the thing in itself, because you're not capable of perceiving it or comprehending it. So what you see are elements of it. So we're going to say, well, that's the thing in itself, it's a schematic representation of it, it's quite complex, and then hypothetically you can see that thing in all the other ways that are illustrated in the diagram, right? So if I asked you what that was, you could say, well, it's a rectangle, or you could say it's a rectangle with 4 rectangles as sub-elements, or you could say that it's, I think that's, what, 24 rows, which it also is, or you could say it's a bounded rectangle that's made out of 2 paths and 4 sub-rectangles, or you could say that it's, I don't remember how many are in there, but you know, that's the most differentiated representation, object 5, and then you might say, well, which of those is the real object? And the answer first would be, well, none of them are. And then the second answer would be, it depends on what you want to do with the representations. And you actually, it's not really obvious that you can make things more real than that. It's like, how real is what you're perceiving? It's real enough for certain operations and not real enough for others. And so, its validity, it's a pragmatic approach, its validity is determined by its applicability in the situation in which you want to apply it. Okay. And then at the bottom there are words, and the words are basically labels for those percepts. So, you know, the first one you could sum up as 432, because I guess there's 432 little circles there, and the second one you could, on the bottom you could summarize as a cross or a rectangle, and the one at the top you could summarize as a flag, and you get the point. So the word is representing a percept that's already simplified, and that's representing something that's more complex underneath it. Okay, so here's another way of looking at it. So if you're looking at a computer, your computer crashes, we'll say. So you're working on your computer, and then you might think, well, are you actually working on your computer? And the question, the answer to that is, it depends on exactly what you mean by computer, and exactly what is this thing that's a computer. So actually when you're working on a computer, what you generally see is only the screen, and you don't even see the screen. You see that tiny sub-element of the screen that contains those representational entities that are directly relevant to the area of the world that you're focusing on right now because you want something to happen. Okay, so really when you're interacting with the computer, you're just interacting with this tiny little part of it. And then the problem is, in order for that tiny little part to maintain its validity as a representational entity, all the things that you don't see about the computer have to work. Right? And then you might think, well, what don't you see about the computer? Well, that's what this diagram is supposed to be showing. So the first thing is you don't see the elemental properties of the computer, and that would be its existence at a quantum level. And that actually turns out to be increasingly relevant for computer designers. Because, you know, you cannot specify the location and the momentum of a particle at a quantum level with 100% accuracy. And what that means is it actually has relevance. The little wires in computer chips are getting so small now that there's some reasonable probability that an electron you think will be in the wire is outside the wire. And that means they'll short out. So at some level of interaction, the quantum properties actually matter. Okay, so that's part of the computer you don't see. And then, well, the computer itself is made out of all these little parts that are as complex as little cities, and it's just packed with that. And what you don't know about that could fill whole volumes, and any of those things can, you know, malfunction at any moment, so that's a big problem. And then those micro parts are arranged into subcomponents. With a desktop, maybe your sound card is gone, or your video card is gone, or something that you could take out and replace if you could only specify the proper level of analysis. Or, you know, maybe you bought a lousy brand, and that's the problem. You bought some cheap computer that's made in a dismal factory, and the probability that it's going to be reliable is 0. And then you might ask, well, why is it that that brand is not reliable? And you might say, well, the economic system within which it was produced is corrupt, and so is the political system. And so as a consequence of that, people can get away with shoddy manufacturing, and that manifests itself as the fact that your computer crashes in the middle of an essay. And then you might say, well, what's the right level of resolution to solve that problem? And the answer to that is, that's not obvious. It depends on what you mean by solve it. Now, usually what you mean is do the minimum necessary to get the system back online so that you can return to your activities. But it's by no means obvious that that's always the right solution, and sometimes it isn't, because at some point you're going to say, well, I should just throw the computer away. And you know, if you own computers, that when to throw them away is actually a complicated problem. How many of you have like 3 or 4 old laptops lying around the house? Right. So like, why? Well, they still work. Well, do they really? And then a deeper question is, what makes you think that they're still laptops? And the answer to that is, well, they look like laptops, and that's also wrong. They look like laptops if you think that a box is a laptop, and it's not. And with computers, you can really see this, because you can have an entity that's fully functional, a laptop, and then if you just leave it on your desk and don't touch it for 5 years, or let's say 10 years, what is it then? Well, it's become so disconnected from the ecosystem that it's a part of that it might not be useful for anything anymore. You might not even be able to get it to work. And you know, most things around us don't change that fast, so we can perceive them in relatively simple forms, and they don't transform so quick that shows us that our perception is gone astray. But computers aren't like that. They transform so rapidly, you probably spend 1/5 of your time just trying to keep up with the transformations.